Next topic is polytropic processes. These are the processes which has constant specific heat. And if the process do not have the constant specific heat, that is they have the variable specific heat, then the processes are known as the non-polytropic processes. Different processes which we have discussed already, like isobaric, isothermal, isochoric and adiabatic processes, all these processes have the constant specific heat and are known as the polytropic processes. Polytropic processes mathematically can be written as PV raised to power x equal to constant. Here x is called polytropic index and its value is given by x equal to C minus, this is the specific heat, molar specific heat, minus Cp, that is the molar specific heat at constant pressure, divided by C minus Cv. Because for the polytropic processes, all C, Cv and Cp are constant, so we can say this x is also constant for a particular polytropic processes. We can derive this relation using the first law of thermodynamics. First law of thermodynamics states that dq heat supplied equal to du change in the internal energy plus the work done. dq can be defined as the number of moles multiplied by the molar heat capacity C into dt, and it is equal to du, this is the change in the internal energy, and it is defined as n into Cv dt plus, and work is pdv. Using the ideal gas equation, which is PV equal to nRT, and if we differentiate it, we will have PdV, taking the pressure first constant and then taking the derivation of second, and then taking the second variable as constant and differentiating the first, it is equal to nR, these are the constant parameters, into dt. So dt is equal to pdv plus vdp by nR, and this dt can be substituted here. Here we can write it is n C minus Cv, if we bring this NCV dt on left hand side, and it is dt equal to pdv, and replacing dt with the value pdv plus vdp by nR, we will have n into C minus Cv into pdv plus vdp by nR, that is equal to pdv. Here n get cancelled, and simplifying, first this r is taken on the right hand side, and simplifying we will have, this is C minus Cv into pdv plus vdp, so we multiply it and we will get C into pdv plus C into vdp minus Cv into pdv minus Cv into vdp, and that is equal to prdv. Combining the terms having the parameter pdv, and this is also pdv, so we will have, it is C minus Cv, and if we bring this right hand side term on left side, it will also become minus, it is minus R into pdv. And similarly, taking the vdp term together, we will have C minus Cv into vdp equal to 0. Or we can write, dividing the equation by C minus Cv, we will have C minus Cv minus R divided by C minus Cv into pdv plus vdp equal to 0. And now using the equation that Cp minus Cv equal to R or Cp equal to Cv plus R, we can replace this Cv plus R equal to Cp, and hence we will have C minus Cp divided by C minus Cv into pdv plus vdp equal to 0. Further, we divide both sides by pdv, and we will have C minus Cp by C minus Cv into P by V. This is dV by V plus dP by P, and that is equal to 0. Now integrate it. On integrating, we will have this term is constant, so it is taken out of the integral, and integral of 1 by V with respect to V is the log of V, plus similarly the integral of P 1 by P with respect to P, it is the log of P, and the term will be here constant. This is the constant of integration. Here we replace this term as x. Let x equal to C minus Cp by C minus Cv. So we will have x log V plus log P equal to constant, and using the property of logs, it can be written as log V raised to the power x plus log P equal to constant, and further it is log m plus log n, that is log mn, so we can write it is log pvx equal to constant, because pvx, if we write, it can be written as e raised to the power constant, and e raised to the power constant is itself a constant. Therefore, finally we get a relation for the polytropic processes, that is Pv raised to the power x equal to constant, where x is the polytropic index and the value derived is C minus Cp by C minus Cv. Here C is the molar heat capacity of the process, Cp is the molar heat capacity at constant pressure, and Cv is the molar heat capacity at the constant volume. This modulation index x equal to C minus Cp by C minus Cv further can be elaborated as C minus, because Cp equal to Cv plus R. So we substitute the value here, Cv plus R divided by C minus Cv, and opening the bracket, it is C minus Cv plus R by C minus Cv, and it can be done as 1 plus R by C minus Cv. Therefore, R by C minus Cv, on rearranging, we will have 1 minus x, or we can write C minus Cv equal to R by 1 minus x. Therefore, molar heat capacity of the polytropic process can also be written as C equal to Cv plus R by 1 minus x. As we know that Cv is equal to R by gamma minus 1, therefore we can write C equal to R by gamma minus 1 plus R by 1 minus x.